Okay, grab your inflection point and uh, turning point packet. We're going to take a look at a few problems. Uh, so you got your worksheet and you got this guy, these three ones right here. In fact, it's actually easier to look at the one in the middle first and see what's going on. So they have this first graph right here. This is the actual function, and you can see it. It's a cubic function, 2x cubed, and then up at the top, um, this is the graph of its derivative. And knowing what we know about derivatives now, it shouldn't be surprising that we're going from 2x cubed minus 6x squared plus 6x minus 3 power rule brings us to the derivative right here. So this is not, should be able to handle that. So what we're going to focus on now is we already know that finding the turning point, we can set the derivative equal to 0 because the derivative is the slopes in the horizontal line. Derivative, take the derivative, set it equal to 0. You find your values of the turning points. But what we can see here, they're trying to show you that this is an inflection point, which we talked about the other day. It's where it changes from concave down to concave up. And what you want to look at here is the inflection point. When you take the derivative, it turns into a turning point, which this is then x. And if you go over to this one on the right, we have, again, a cubic. This is the f of x function. This is the derivative function. So we have the inflection point, that's where it changes from concave down to concave up. When we take the derivative, that same x value turns into a turning point. And knowing what we learned about how you find turning points, the moral of the story here is, how do you find an inflection point? You actually take the derivative of the derivative and set it equal to 0. Because if the first derivative is a turning point, from an inflection point goes to a turning point, what do we do to find a turning point? We take the derivative and set it equal to 0. So if you look at the problems down below, number 5, which is exactly, it's these problems right here. So I'm just going to use these ones over here. Here's the original function. There's the derivative. Here is the second derivative, which we do with a double prime. And the second derivative would be equal to 2. Now, I ignored this one right away because I said there is no inflection point. And if you take the second derivative for this one, which is 2, and set it equal to 0, this does not exist. And since 2 is not equal to 0, we say that there is no inflection point, no IP. This one here, first derivative from the original function, 6x squared minus 12x equals 6. Take the second derivative of it. That's going to give me the value of this turning point. I know we can see it, but you're not always going to get the graphs, like hardly ever. So we get 12x minus 12. Now I take 12x minus 12, set that equal to 0, because again, we're taking the derivative of the derivative, because the inflection point turns into a turning point. How do we find a turning point? We set it equal to 0, because that's the slope of the turning point, and I get 12x equals 12, x equals 1. Plug back into the original function, always back into the original function. That's going to be a real key on these problems. And I'm going to get f of 1 in this case will be 2 minus 6 plus 6 minus 3. That's 2 minus 3, that's negative 1. So I get 1, negative 1, which we should have been able to see up there. But this is how you do it algebraically by using the derivatives, which is going to be useful as we continue. Last one, here's my original function. Take the derivative, the inflection point turns into a turning point. Take the derivative of the derivative, second derivative, 6 x. Set that equal to 0, 6x equals 0, x equals 0. My inflection point is at, plug it into the original function, f of 0 equals 0, and I get 0, 0 for the inflection point. So the first derivative set equal to 0 gives you the turning points. The second derivative gives you the inflection point. Next, how do we classify extrema? We said the other day that we had possible turning points. You find those x values. You classify the extrema by looking at what is happening with the slopes. A possible turning point is a relative max. It's a maximum. If the slope at a point to the immediate left of the possible turning point is blank and the slope at the point to the immediate right is blank. Think about a maximum. We're going up, we're coming down. Here's positive slope, here's my slope of 0, here's negative. So we're looking for positive slope, and then to the right is negative. We have a minimum. Again, I'm coming down, I zero out, I'm going up. I got negative, I got positive. And then it's a possible turning point. The problem is going to come in when we get a possible turning point is actually an inflection point. And then we have a turning point right here. I have negative slope followed by negative slope. I'm going down and I'm going down. And then I'm going inflection point here. I'm going up and then I'm going up. So a possible turning point is an actual inflection point if immediately to the right and to the left are the same, also known as equal. Okay, determine whether each possible turning point is a relative maximum or a relative minimum or an inflection point. And when we're talking about the slopes to the left and the slopes to the right, all we are talking about is the derivative, because we're talking about slopes. Take the first derivative. I think I skipped the increasing and decreasing worksheet. That was just a review of interval notation. We'll do it right here. You can go back and do that. I'm sure you're looking forward to it. 2x plus 6. The first derivative is 2x plus 6. Remember, this is the values of the slopes everywhere. So what we do then is we make a table. Nice looking straight line. That's beautiful. Get rid of that. We're going to make a table. So we're going to go like this. And I'm going to call this negative 3, or excuse me, yeah, negative 3. What are values immediately to the left of negative 3? Hey, how about negative 4? Plug that in. What is the derivative? This will give me the slope at the point. It's what we just got done doing. 2 times negative 4 plus 6. I get negative 2, it's negative. Immediately to the right, I'm going to put maybe negative 2. Hey, how about 0? 0 is your friend. So I put negative 4 in for that one. I put 0 in there. Use 0 whenever you can. The derivative at 0, because it's to the right to negative 3, no big deal. And then I get 0 plus 0 plus 1, and I get 1. So I know it's going to be positive. So if I am negative followed by positive, I know I'm going down followed by going up, which means negative 3 is a relative minimum, which if we looked at the original function, I have an x squared and it's positive. I should know from being in this class that it's a parabola that it's going to open up. Next, we got possible turning points at 2 and negative 2 and a possible inflection point at x equals 0. So I'm going to make a table again, and I'm going to say I got 3 different guys. Now, grab them all. Negative 2, 0, 2. Start to the left. First thing I need to do is take the derivative. 3x squared minus 12. Second thing I'm going to do is put in negative 3, f prime of negative 3, which is 3 times negative 3 squared minus 12, which is 3 times 9er, 27 minus 12. Clearly it's positive. Next, put in a negative 1, f prime of negative 1. 3 times negative 1 squared minus 12. 3 minus 12, it's negative. Next, put in a 1. Hey, it's going to look a lot the same. Negative. Next, put in a 3. Hey, it's going to look a lot the same as the first one that I did. I get 27 minus 12. I get positive 15. And I get positive. So if I have a positive followed by a negative, I got to have a max at negative 2. A negative followed by a negative, I got to have an inflection point at 0. And a negative followed by a positive, I got to have a minimum at 2. So you can tell exactly what they are. If you wanted to figure out what the actual points were, you would plug those values back in. Okay, we're going to move on. I'm going to skip that one. I think you get the gist of it. And we get to these big dogs, which is really the nuts and the bolts of what you have to do and something that I would expect to see on a quiz. We'll do a couple of these and then you can finish the rest of this packet. Again, there will be a quiz coming up in your near future. 1, find the possible turning points. 2, find the possible inflection points. 3, find the ordered pair of the actual. 4, identify the intervals of increase and decrease. That's the interval notation that I'm talking about. And 5, sketch the graph of the function. How do we find possible turning points? We're going to take the first derivative, set it equal to 0. How do we find possible inflection points? Second derivative, set equal to 0. Identify the actual, make the table, then plug in values into the first derivative. And then how do we find the intervals of increase and decrease? You'll use the table like we just made. Sketch the graph. We'll take a look at how to do that in a moment. First thing I'm going to do is I'm going to take the first derivative and I'm going to get 2x minus 4. Then I'm going to set that equal to 0. And I'm going to have 2x minus 4 equals 0, 2x equals 4, x equals 2. Next, I'm going to take the second derivative, which is 2. And I'm going to set that equal to 0. That's impossible. Duh. No IP. Then we need to make a table. And we'll use that. We'll make a table. And I've got 2 is all I've got. And I'll have to the left of my 2. I'm using this guy right here. I have 0, and to the right I have 3. I always use 0 because we're going to put this into, we're talking slopes now. So f prime of 0. F prime is negative 4. So I'm negative. I put a 3 in there. F prime of 3. The table will always be done with slopes because we're talking about increasing and decreasing. F prime of 3 is 6 minus 4. It's positive. This shouldn't surprise us too much. So if I'm down going up, then I'm going to be a minimum. I need to find that minimum. Always go back to the original function. If you're looking for a value on the original graph, f of 2 is 2 squared minus 4 times 2 plus 2. Lots of 2's. 4 minus 8 plus 2 must be, wait for it, negative 2. So I'm going to have a minimum at 2, negative 2. No inflection point. We said that before. So I've covered A and B and C. Identify the increase and decrease. So we are increasing from increasing from 2 to infinity. 2 to infinity. We are decreasing from negative infinity all the way to 2. You can be either parenthesis or bracket at 2. It's kind of interchangeable. Remember, that's where we make our change. But it would be okay if you had the bracket there as well. Say it's included. Last one. Oh, sketch graph. We've got a minimum at 2, -2, 1, 2, 1, 2. There we go. We're increasing going away. If I really wanted to get crazy, I could calculate some zeros, or I could find another point, plot it up. So I could go put a 0 in there, and I get 2, 0, 2, 1, 2. I know I got symmetry here because we got a parabola. But I could put 4 in there, would be 16 minus 16 plus 2. Hey, there you go. And we have a ugly looking parabola.